Okay, so I just made the other video, but they're a day apart, even though it's 5 minutes for me. So now we're jumping into spherical coordinates, which is the last set of coordinate systems that we have for triple integrals or anything for that matter. And so in the last video we showed that so let's recall, if we're integrating this thing, in rectangular coordinates we have dx, dy, dz, or some iteration of those three, and x, y, and z are those are three lengths. And then in cylindrical coordinates we have dz, r, dr, d theta, which is two lengths and one angle. And now for dv in spherical coordinates, now we're on a sphere instead of a cylinder, we have two angles. We have two angles and one length. And dv is crazy because here's what it looks like. It's rho sine of phi. That's the r in the other, so that's the r in this integral. It becomes rho sine of phi d rho d phi d theta. All right, and so the big question is, where does this rho sine of phi come from? Well, I made a deal with you guys and with myself. In some video, I think it was like video 18, I showed how the r appeared when we did this. And it was really intense. I had to build these little sectors that looked like this, and they had a little height, and we had to put it on a thing, and I had to figure out that. And after all that work, Riemann sums and everything, the R appeared, not magically, through a lot of work, and it was super cool. And I said, I'm going to do it for this, but I don't need to do it. It's the same construction, but now instead of being on a flat sector, it's on a curved sector. So now the bottom is also curved. And when you do an insane amount of algebra and geometry, what you wind up with is, instead of having an r pop out, you have this rho sine of phi pop out. And that's the dv in this game. Okay. All right, so piggybacking off the last video, in spherical coordinates, points are represented by, like I said, one length and two angles. So the length is rho, and the two angles are phi and theta. And some people write phi like this, and I feel like these are both phi. I've always written phi this way. It's sort of the cursive way, but either's fine. The bar through the angle needs to be vertical, whereas in theta it needs to be horizontal. Okay. All right. And so if you're integrating a function over some d, you have the function, which is a function of rho, phi, and theta. Then you have the r, which is the sine of phi, d rho, d phi, d theta. Okay, so let's look at what the hell's going on here, right? So we have, again, same as the last pictures, there's a point out here called P, okay? And it has coordinates rho, phi, and theta. If you project this down onto the XY plane, right, and you run a line out like that, and then you say, all right, let's put this here. So the distance from the origin to the point, that's our only length, that's rho, right? So that distance is rho, okay? The angle off the x-axis to here, that's theta. And the hardest part of this thing is that the phi is this angle. It's the angle off the positive z-axis. So phi is here. Okay? And, you know, when this works, it makes life really simple, but it doesn't always work. You need to be on a sphere. That's why they're called spherical coordinates, because points on a sphere have this setup. And believe it or not, of all of these, so if I did a thing with the MT department ages ago, and they talked about spherical geometry, and I was like, "You guys do spherical coordinates?" They're like, "Yes, Dr. Pullman. Do you know what those are?" And I was like, "Well, yeah. Do you?" And then they showed me their book, and okay, it's spherical coordinates. But when you think about flying, right? When you fly, you're on a sphere. And so most guidance systems on planes use spherical coordinates. And I guess ships do too, because they're also going on a sphere as well. And it's pretty cool because the angles make things clear when you're actually on a curved surface that's spherical or semi-spherical. All right, so just like before, there's a relationship between the rho, the phi, and the theta, and x, y, and z. So let's see if we can't figure that out. I'm going to get better colors here. So we're going to do what we did before. So this distance is x. This distance is y. Where's my good picture here? I have a really good one here. Yeah. Nope. Okay. Now check this out. If now we're going to juxtapose all three of these together. If we're working in cylindrical coordinates, this distance was r along here. Right? This distance is z. The angle theta is the same in both cylindrical and spherical coordinates, so that's nice. And if you start messing around with, like for example, this angle is pi over 2 minus phi. If you play with all these, you put a line here, that's r. If you play with all of these and just do a bunch of trigonometry, you wind up with this cool set of relationships that in rectangular coordinates we have x. In cylindrical coordinates we have r cos theta, and in spherical we have rho sine phi cos theta. Similarly, in what we have in xy coordinates, rectangular coordinates, we have y. In cylindrical coordinates, we have r sine theta, and in spherical coordinates, we have rho sine phi sine theta. And these are the sort of go-betweens for all of these. And if you look if you look over here as well, you get that z equals rho cos phi, and that comes from this relationship here. You got the length of z here, and you have that. And you also have that rho is the square root of z squared plus r squared, which is the square root of z squared plus x squared plus y squared, which puts you on a cylinder, right? Because rho squared is going to be on the cylinder. And if all this is, confusing, I am notorious for asking you to set up this whole relationship right here on quizzes and explain to me why one of these things is true and one isn't. So, but they're all related. You just got to use your trig and be very organized to find those. And I have a great worksheet that I'll post right below the video on the blog. And that's really what you want for these quizzes. It's just got everything I just said here all in one place and set up well. So, all right. Well, let's look at some example that might probably have spherical coordinates and figure out if we can't can't tell. So we're going to find the volume of the solid D cut from the sphere rho less than or equal to 1 by the cone phi equals pi over 3, right? So in spherical coordinates, if you fix rho, you get a sphere, and if you fix phi, you get a cone, and I'll show you why in a second. All right, so let's think about this. We have y, x, and z. So if rho equals 1, we have a sphere of radius 1. Right, these are all ones. And then if phi is fixed at pi over 3, that means rho and theta are free, right? So here we have rho is free and theta is free. That's what makes it a cone. I'll put some colors here. Right? So if phi is pi over 3, we come down here pi over 3, which is 60 degrees. So that shoots this guy out like that. And the other two, so here's phi doing its thing. It's getting as big as it's want. And I can also spin around like that, right? Okay, so let me get my pencil right here. So all that survives, so the bottom is the cone. All this gets cut away. And this is literally an ice cream cone. The bottom is a cone, and the top is a sphere. Like that. Okay? All right. So let me get rid of this space here. Clean it up. How do we find these bounds? So what we do is we emanate array M away from the origin and look for intersection points. So as we exit the origin here, so we start at rho equals 0 and we go out the top here and we exit there. So there's my M, right? So rho goes from 0 to 1. Because we're on the sphere, rho equals 1. Okay. And then we look at the angle phi, and phi starts here on the z-axis and opens outward. So phi goes from 0 to pi over 3. And then lastly, if you project this thing down, theta goes from 0 to 2 pi. And then we put in our integration friend, and then we have d rho, d phi, d theta. All right. And well, that's pretty darn cool. Did I finish this? It looks pretty boring, but it's probably a good idea. I'll make this guided practice. Finish this problem. Right? So you're going to integrate with respect to rho first, and then phi, and then theta. And you should get something really nice. And because this thing, well, you got to be careful when you do this. This is why a sketch helps. Because this thing is symmetric with respect to the z-axis, on your last step, you could probably go, theta could go from 0 to pi over 2, and then multiply by 4 out front. In fact, I'm certain you can, yeah, because they're symmetric. And that helps in the end because I guess it just makes it a little easier. All right. There's lots of shortcuts to take, but it's never a good idea to shortcut when you're doing this. So, all right. Well, let's see if I have another one here. I hate to quit this early, but here's another example. Here you go. Here's a sphere that's off of the origin. So if you have a sphere, x squared plus y squared plus z minus 1 squared equals 0, and you want to put this into spherical coordinates. Well, okay. Squaring the z minus 1, you get that this guy is, okay, rho squared minus 2z plus 1 equals 0. No, that's wrong. Where the hell is that? Here it is. Can't be equal to 0. So you have, this is supposed to be, sorry. This is supposed to be 1. So it's a sphere of radius 1 centered at 0, 0, 1. And so there's a 1 here, and then a 1 here. So now you have rho squared minus 2z equals 0. So that rho squared is equal to 2z. And z is rho cos phi. That's from that worksheet. Now rho is equal to 2 cos phi. And that gives you the equation of that sphere. So you have to do this kind of stuff when you're finding the limits of integration, because all the x, y's, and z's need to disappear. So do the r's, but the theta can stay. All right, well, a lot of this is going to really take place via talking and the workshop on Friday, because yeah, it's in the devil's in the details with this, and you'll see there's a lot that can happen. But make sure you download that PDF with all the relationships, and have that handy when you're actually doing these problems instead of searching for crap on the internet, because it's got everything you need for this. And if you think you need more, you're probably doing it wrong. So that's all I got. I'll see you in a little bit.